In this video, we're going to focus on Bayes' theorem. But first, let's go over some formulas, particularly with conditional probability. The probability of event A occurring, given that event B has already occurred, is the probability that event A and B will occur divided by the probability that event B will occur. Likewise, we can say that the probability of B given A is equal to the probability of B and A occurring divided by the probability that event A will occur. Now, the probability that event A and B will occur is equal to the probability that event B and A will occur. So basically what I'm doing is I'm setting these two equal to each other. Now, this is equal to the probability of A given B times the probability of B. So let's replace that on the left side. Now on the right side, the probability of B and A occurring is the product of the probability of B occurring given A has already occurred times the probability of event A occurring. Now what I'm going to do is divide both sides by the probability that event B will occur. And so this is going to give me the formula that is associated with Bayes' theorem. So the probability that A will occur given that B has already occurred is equal to the probability that B will occur given that A has occurred times the probability of event A occurring divided by the probability that event B will occur. So Bayes' theorem helps us to calculate the conditional probability of an event if basically you know the reverse conditional probability with some other probability values as well. But this is the basic formula of the Bayes' theorem. So P of A given B is equal to P of B given A times P of A divided by P of B. Now let's use a simple example that will illustrate the use of Bayes' theorem. So let's say that in a bottle, there's a bunch of pieces of papers with numbers on it. Let's say event A represents the following numbers being drawn: 1, 2, 3, 4, and 5. Now let's say event B represents the numbers 4, 5, 6, 7, 8, and 9. Now, what is the probability of A given B? Let's use Bayes' theorem to calculate this particular probability. Even though we don't need to for educational purposes, let's do it. Now, what I'm going to do is create a Venn diagram. So let's say the first circle is for event A, the second one is for B. So A and B has these two numbers in common, 4 and 5. So that's the intersection of A and B. A also has the numbers 1, 2, and 3. B has the numbers 6, 7, 8, and 9. Now, in order to calculate this using Bayes' theorem, we need to know the probability of event A occurring, the probability that event B will occur, and basically the reverse conditional probability, the probability that B will occur given that A has already occurred. So what is the probability that A will occur? Well, we need to write the sample space. The sample space represents all of the possible numbers, the numbers in A and B. So the numbers that we can get represent all of the natural numbers from 1 to 9. So A has 5 out of the 9 possible numbers that we can choose from. So the probability that event A will occur, assuming that each number has an equal chance of being drawn out of the bottle, is going to be 5 out of 9. Now B has 6 numbers out of the 9 numbers here. So the probability that event B will occur is 6 out of 9. Now what about the next one? What is the probability that B will occur given that A has already occurred? There's a formula for that. A has 5 elements. It has the numbers 1 to 5. Out of those 5 numbers, there's only 2 numbers that is in B that is part of A. So the probability that B will occur, given that event A has occurred, is 2 out of 5. So now, with this information, we can calculate this particular conditional probability. The probability that A will occur, given that B has already occurred, is going to be P of B of A, or rather B given A, times P of A over P of B. And let me get rid of this. So P of B given A, that's what we have here. That's 2 over 5. Times P of A, which is 5 over 9. Divided by P of B, which is 6 over 9. So right now, we could cancel the 5s. And if we multiply the top and the bottom of the fraction by 9, we can also cancel the 9s. So we're left with 2 over 6, which reduces to 1 over 3. So the probability that A will occur, given that B has already occurred, is 1 out of 3. Now let's confirm that using conditional probability. So P of A given B is the probability that event A and B occurs over the probability that B will occur. So we know that the sample space has 9 numbers. How much of that is A and B? The intersection of A and B is basically 2 numbers, 4 and 5. So the probability that event A and B will occur is 2 out of the 9 possible numbers. Now the probability that B will occur is what we see here. It's 6 over 9. So multiplying the top and the bottom numbers by 9, we're going to get the same result. Initially, it's going to be 2 over 6, which reduces to 1 over 3. Now granted, we could have done this from the beginning, but now you see how Bayes' theorem works with the formula that we wrote earlier. But let's consider another example in which we could use the Bayes' theorem formula. A particular study showed that 12% of men will likely develop prostate cancer at some point in their lives. A man with prostate cancer has a 95% chance of a positive test result from a medical screening exam. A man without prostate cancer has a 6% chance of getting a false positive test result. What is the probability that a man has cancer given that he has a positive test result? Go ahead and try this problem. Feel free to take a minute if you need to. So let's write down what we know. The probability that a man has cancer, I'm going to write P of C, is 12%, which is 0.12 as a decimal. Now, the second sentence says that a man with prostate cancer has a 95% chance of a positive test result. So, given that the person has cancer, the probability that he will get a positive result or positive test result is 95% or 0.95. Now, what about the third sentence? A man without prostate cancer has a 6% chance of getting a false positive test result. So the probability of getting a positive test result given that the person does not have prostate cancer is 6% or 0.06. So what is the probability that the person has cancer given that he has a positive test result? That's what we need to find. So let's write the equation for that using Bayes' theorem. So this is going to be the reverse conditional probability, which is the probability of getting a positive test result given that the person has cancer times the probability that the person has cancer divided by the probability that the person has a positive test result. Now, we have these two values already, but we don't have this one. How can we find it? In this case, it's going to be very helpful to make a tree diagram. So 12% of the population will have prostate cancer based on this particular study. That means that 88%, which is 100 minus 12, or 0.88, will not have cancer. Now, out of those who have cancer, 95% of them will have a positive test result, which means the other 5% will have a negative test result. Now, out of those who do not have cancer, 6% will have a positive test result, which means the other 94% will have a negative test result. So using this tree diagram, how can we determine the probability that the person will have a positive test result? The probability that a person will have a positive test result depends on two events. That is the probability that the person has cancer and they will have a positive test result, or, which will be represented by the addition symbol, the probability that the person does not have cancer and has a positive test result. Those are the two options. So the probability that the person has cancer and has a positive test result is the product of these two values, where they will have cancer and have a positive test result. So it's basically 0.12 times 0.95. The probability that the person does not have cancer and has a positive test result is the product of these two values. So it's 0.88 times 0.06. 0.12 times 0.95 plus 0.88 times 0.06, that's equal to 0.1668. Now I'm running out of space, so I'm going to have to delete a few things. Hopefully you wrote that down because I'm going to refer to it later. If not, you can always rewind the video. Now let's plug in the numbers into this formula. So the probability of getting a positive test, given that the person has cancer, that's 0.95. The probability that the person has prostate cancer is 12%. And the probability that the man or a man will have a positive test result is going to be 0.1668, or 16.68%. So it's 0.95 times 0.12 divided by 0.1668. And so you should get 0.68345. So there's approximately a 68.3% chance that the person will have cancer given that they have a positive test result. So what is the probability that the person does not have cancer even though they have a positive test result? That's going to be 100 minus this number, 0.683, which is 0.317. So there's approximately a 31.7% chance that even though the person has a positive test result, that they do not have cancer. So sometimes, even if you get a positive test result, doesn't mean that you have that condition. There's always a risk factor. But the answer that we're looking for in this problem is this number, 68.3%. Now, there's another way in which we can get that answer. And let's talk about how we can do it. So let's say that there's 10,000 people in a city. And based on this survey, 12% of those individuals have cancer. So we're going to use the same percentages. 10,000 times 0.12 is 1,200. And the other 88% do not have cancer. So 10,000 times 0.88 is 8,800. Now, of those who do have cancer, we know that 95% of them will get a positive test result. So 95% of 1,200, or 1,200 times 0.95, that's 1140. So the other 5%, that's 1,200 times 0.05, will get a negative test result. And so that's 60. Now, of those who do not have cancer, we know that 6% of that population will get a positive test result. So 8,800 times 0.06, that's 528. The other 94% will get a negative test result when they don't have cancer. So 8,800 times 0.94, that's 8,272. So now let's see if we can use this information to get the same answer. So let me clear away a few things. So the probability that a person has cancer, given that the person has a positive test result, is going to be, well, let's break it up into two parts. Based on the number of people that we chose, it doesn't matter if you chose 10,000 or 100,000. Because we're dealing with a ratio, it's still going to be the same. Out of this group of 10,000 people, how many have a positive test result? The amount of people that have a positive test result is the sum of those two numbers. It's 1140 plus 528. Now, out of those who have a positive test result, how many of them have cancer? It's only this number. That's the number who have cancer and have a positive test result. So that's 1140. So let's go ahead and add 1140 plus 528. So that's 1668. So 1140 divided by 1668 gives us 0.683. So we could see why the answer is the same. There's a 68.3% chance that the person will have cancer given that they have a positive test result. So now you see two ways in which you can get the answer. Using a tree diagram or using the formula associated with Bayes' theorem.